All right, we're back. We're still on page 3 of notes 20, I think. Yep, of Calc AB. We're doing areas of regions bounded by curves. And now what we're talking about are horizontally simple regions, which means a horizontal line passing through the region intersects the left and the right. The left and the right curves never switch. Vertically simple means a vertical line passing through the region. The top and bottom curves never switch. And depending on which type of region you're dealing with, you might want to integrate with respect to x. Integrating with respect to x is like the normal thing, like the thing that like feels the most natural. You're gonna get dx, you're gonna go from left to right on your bounds, you're gonna go top take away bottom, feels the most normal. With respect to y is like bizarro world where you're always doing right take away left for your integrand because you need to get a positive value for the kind of like the base of your rectangle. Your delta y's are cutting up the y-axis, so you go from the lowest y value to the highest y value as the bounds of your integral. I mean, it makes sense, but it like feels a little weird. So let's see, we want to do these in the best way possible. So like you're not being told you have to use dy, but maybe you do, or maybe you want to. I don't think you ever like have to. It's just a question of how much work you want to do. So here, I look at this and I think this is classic dy. And the reason that it's classic dy is I don't want to solve these for y. And if I'm going to integrate with respect to x, I have to get y equals your function of x. Here I have a squared, whatever. Here I have a fourth. Nothing about integrating that sounds like it's going to be super fun. So what I'm going to do is I'm going to say that this is x equals 4 minus 4y squared, and I'm going to say this is x equals 1 minus y to the fourth. X is going to be greater than or equal to 0, which means we're to the right of the y-axis, which like is probably a good thing, but who knows. So let's see what these look like if we can get a sense of it. Here. Actually, like I think they intersect like a lot. Anyway, this is definitely a parabola. So like if y is equal to 0, then we get x is equal to 4. So let's do that, 4. If x is equal to 0, then we get y is equal to plus or minus 1. So let's do that. And then let's just fill in a curve between them. I mean, it's a parabola. So we have this. Okay, so this is x equals 4 minus 4y squared. All right, let's do the same kind of reasoning here. If y is equal to 0, x is equal to 1. So we're like well inside here. If x is equal to 0, then y is also plus or minus 1. So go here, here, and here. And I think these intersect again over here somewhere. It doesn't really matter, but I feel like they should, but I'm not really sure. But you would like set them equal, and then you'd have to like solve something. Better to just go with what we have. So we're dealing with this region. So this region, if you'll indulge me for a second, I'm gonna actually like make a vertical line and pass it through the region. So this line, you can see as it passes through the region, like the top and bottom curve are like kind of consistent here, but then we reach here and suddenly there's an issue. Like the top and bottom curve, you need multiple integrals to even kind of deal with this. This is not a vertically simple region. So what I'm gonna do is I'm gonna cut this, and then let's take a look at a vertical line. God, man. This is the point where if you're in Algebra 1, I used to teach Algebra 1, I confuse the words vertical and horizontal like all the time, and that's like a major part of Algebra 1. It's like vertical lines and horizontal. They're not great. Here you can see this horizontal line never has a problem. The right and the left curve never change all the way through the region. So right takeaway left is the way to go. So let's see if we can do it. So I'm going to go with the integral from the lowest y value is -1, the highest is +1. This region is actually kind of like an even, it's like an even region with respect to the x-axis, like reflecting over it, but like I'm not going to, you could do 2 times the integral from 0 to 1 and get your answer. I'm not going to do that though, because I think it's a little more confusing. So right-hand curve minus left-hand curve, and then dy. All right, we should clean this up before we try to do it. So 4 minus 1 is 3, and then we'll just get minus 4y squared plus y to the 4th. Fundamental theorem, straightforward, I think. 3y minus 4/3 y cubed plus 1/5 y to the 5th, negative 1 to 1. Should have done, this is why you want to double it and go from 0 to 1, because you get to plug in 0 and like life is a little better. 3 minus 4/3 plus 1/5 minus, then we get negative 3 plus 4/3 minus 1/5. So we're just getting 2 times the original thing, but that's all right. We get 6 minus 8/3 plus 2/5, 15. Great. 90 minus 40 plus 6, I think, over 15, 50, 56 over 50, possibly 56 over 15. All right, we can knock that out on a calculator pretty quickly, and then we'll find any errors that I made. Let's take a look at the next one, though. All right, x equals y to the 1/3. X equals y to the 1/5. So here's the question that you have to kind of like ask yourself. I mean, like, this is fine. And I know what a cube root looks like, but I know what a cube root looks like for x, not necessarily for y. And then here, x equals y to the 1/5. There's actually some, because the names of the variables don't matter, you could literally just switch this and say this is y equals x to the 1/3 and y equals x to the 1/5, and they'll just do that problem. They'll have the same exact area. I don't think it's really the spirit of the problem, so I'm not going to do that. But like, you could. It's just like spelling it differently, right? Like this. What am I doing here? Like this region here has the same area, no matter. I was going to rotate it, but like apparently I can't do that. If I rotate it without changing the size, it still has the same area. So like I could just spell the problem differently and say it's y equals x to the 1/3, y equals x to the 1/5, deal with it. What I'm going to do instead is I'm going to cube both sides of this and say that y equals x cubed. I'm going to raise this to the 5th and say this is y equals x to the 5th. And then graph those, because I do know what those look like. Also, I think this is like an easier problem in my brain. So x to the, is there like, oh, there's no, do these intersect more than once? Probably. Let's do that. X cubed equals x to the 5th. X to the 5th minus x cubed equals 0. X cubed, x squared minus 1 equals 0. So x is 0, x is 1, and x is negative 1. Interesting. And there's like nothing in the problem that would restrict any domain type things. So here we go. X cubed is like this. Then x to the 5th is like tighter, right? X to like 10,000th would be like basically like x to the 10,000th looks basically like this. Like not exactly like that, but kind of. Like graph it on your calculator, you'll see. So x to the 5th is doing this, I think. So I think this, in a world where I have an infinite number of colors, why don't I use more than one? Okay, hold on. I may have overdone it there. Redo that. There we go. Okay, so x cubed, I will say, is like this. I'm going for like extremes. This is y equals x cubed. X to the 5th, then we'll do this, more or less. This is y equals x to the 5th. All right, so these two regions are exactly the same if you do it correctly, which I clearly haven't, but they are the same. So what I'm going to do is I'm going to find one of them and then just double it. So we'll do this. I'm going to do 2 times the integral from 0 to 1 on the x-axis. The top curve is x cubed. The bottom curve is x to the 5th. And then dx. I think that's going to work. I mean, I always say something like that, and it's like, yeah, I mean, I'm trying to teach you how to do it. I better hope it's going to work. But it's often actually literally just me hoping. I mean, I know what I'm doing, but then minus 0. Okay, so this is maybe not bad. 12 again, 3/12 minus 2/12 is 1/12. So 1/6 potentially. I think that area is going to be 1/6. All right, let's check both of them on the calculator and then fix the things that need fixing and then go from there. All right. So first thing, I'm just going to do the integral here. Integral of 4 minus 4y squared minus 1 minus y to the 4th, comma y, comma, -1 to 1, 56/15. Woo! I mean, we could probably like graph that and do it, but like, feeling pretty good about that. Let's try the next one. So I ended up doing the integral of x cubed minus x to the 5th. Like, it ended up being a pretty simple integral after a lot of discussion, from 0 to 1, but then I have to double it, so I'm going to put the 2 here, bizarrely. Get 1/6, nice. Let's check it on the, let's try to graph it. So what am I graphing here? I'm going to graph x cubed and then x to the 5th. Oof. And then let's zoom. Try like a, excuse me, zoom box here. There, you can see the regions. You know, graph a lot of things in your life so that you have insights like these regions are going to be exactly the same. But there you go. Okay, so one of them I did with respect to x, one with respect to y. You just have to pick and see which one you think is easier, like given a certain set of circumstances. I thought in this particular case it would just be easier to solve, you know, the one way. And it's up to you. So try it the other way, see if you get the same thing. All right, I'll be back in the next video to do some more. So see you there.